Alright everybody, for this video, I'm going to be analyzing a graph talking about things like domain, range, discontinuity for this particular graph. Probably explain a little bit as I go, then I'll go back and explain more after. That's how I do it. Alright, busy, gotta go. So, this graph, we'll start as usual with domain and range. So when I do domain, I like to think of taking vertical lines, which have the equation x equals k, where some k is some constant, and I scan. As long as it's touching, that x value is in the domain, k is in the domain. So for this particular graph, everything is okay until we get here to x equals -1. If we put a vertical line there, it doesn't touch. Therefore, if we're talking domain, then we're saying x could not equal -1. When you continue to scan, we're still touching this top part of the graph until here. Again, you're not touching, this time at x equals 1. After that, it's got graph values everywhere else, output values for every other input value. Therefore, these are the only two values not in our domain. So it's a good habit to put these in interval notation. So what are the intervals of x values in the domain? Everything up until -1. Then at -1, we've got a gap. Afterwards, it continues until 1. And there's another gap at x equals 1. So you can see this is basically -infinity to infinity with gaps at -1 and 1. Okay, let's go to the range. Same logic for the range, but since we're looking for output values, we're going to scan with horizontal y equals k lines. And all of these lines are touching the graph, so all of these y equals k values are in the range until we get to y equals -1. At -1, there's a gap continuing until y equals 0, at which time it restarts. So in this case, we can't write it as just y is not equal to two values because there's a gap. The range is everything in the negatives until -1. Now in this particular graph, it may look like it touches -1, but since it's got this flattening out, we're assuming that it has a horizontal asymptote here. It never exactly equals -1 as an output value. But however, it does equal 0, as you can see by the dot there. It goes through the origin. So our range is going to restart at 0, and it can equal 0 to infinity. Okay, next, most everything else is related to the x values from here on out. Discontinuities, as we know, they're often related to the domain. What's happening at these values that are not in the domain? We've got huge gaps here. Those gaps are discontinuities. Particularly, they are non-removable infinite discontinuities. Non-removable because they cannot be fixed by just adding one single point, one single pair of input-output values. So they are non-removable infinite discontinuities. We always say where the discontinuities are located here. They are at x equals -1 and x equals 1. And we can go from there and say those are in fact the two vertical asymptotes. Vertical asymptotes are always non-removable infinite discontinuities. Let's spell it right. So we got vertical asymptotes at x equals -1 and x equals 1. We're basically saying the same thing there in the discontinuity section, the vertical asymptote section, but two different ways of saying it. Okay, let's go to increasing and decreasing intervals. So a graph, anywhere it has an output value, must be increasing, decreasing, or constant. Let's write it like this. There's no constant intervals. So we'll just write it out. Increasing when, decreasing when, and it's never constant. So let's figure it out. So if we look at the graph, if we start from the left again, we always start from the left when we're scanning x values. As you go along, it seems constant because it seems like the y value is staying -1, but actually if we zoomed in, it would be slowly decreasing. And now we can really see it's decreasing. Why? Because it's going down. The output values are going from -2 to -3 to -4. It's going down. So it is decreasing on the interval x. We're talking always about increasing and decreasing on intervals of x values. So we don't even have to say it. We just imply that we're talking about x from -infinity until -1. We have to stop at -1 again because the function is not defined at -1. There's another gap. But as we continue after -1 and go up here, and again, we're moving to the right. As we move to the right, the graph is moving down. It's getting lower and lower output values until here, until this point at the origin. Then it's going to stop decreasing and start going up or increasing. So the full information is it's decreasing from -infinity to -1. And then after the gap, after the infinite discontinuity, it restarts and it continues decreasing from -infinity to 0. We always put a square bracket when it stops increasing or decreasing at a specific value, which implies that it must be either increasing or constant after 0. In this case, after 0, it starts going up. 1, 2, 3, 4, 5 into infinity. So it's increasing from 0 until this value here of 1. And then similarly, it's going to be increasing from 1 to infinity. As we see, when we restart, it's going up. -4, -3, -2. It's increasing, and again here, it seems to be going constant, but if you were to zoom in here, you would see the values would be going from -1.01 to -1.001, etc., etc. It's still getting closer to 0, it's increasing, and it's never constant. Okay, a lot of things we're analyzing here. One more thing. Extrema. So local extrema, also called relative extrema, means the same thing, are minimum and maximum values. They're often related to increasing and decreasing intervals because, well, let's look here. Here, if we start at x equals -1 and go to the right, it's decreasing until this point at which it starts increasing. That implies that we have a local extrema here, because a local extrema, for example, a local minimum, is a low point, a point where everything around it is above it, because it's changing from decreasing to increasing. This point is our only local extrema, and it is a local minimum because it is the lowest y value, the lowest output value in this area. So the only local extrema we have is at the point 0, 0. And the language you use here is very specific. We would say it has a local minimum of 0 at x equals 0. So this 0 here is representing the output value of the function. It's representing the fact that we're at y equals 0 here. That is the lowest y value in this area, and it occurs when x equals 0. There are no local maximums because we never have like a high point. Again, it might seem like, oh, this is the high point, but it's going to keep getting a little bit higher and higher. Here, of course, it keeps getting higher and higher, so there's no local minimum, no local maximum, and no absolute maximum or absolute minimum either. And lastly, I suppose we can say this is unbounded. It's not bounded above, it's not bounded below. Now that was a lot. Let me just briefly go through that again. This is a long video, but there's a lot we do when we're analyzing. So think about what you're doing. Most of the things you're doing, you're scanning x values. Domain, you're scanning x values and seeing what's giving you outputs, what's not. Discontinuities, you're seeing where there's a gap in that scan. increasing, decreasing intervals, you're also scanning from left to right, and you're seeing what's happening to your output values. So again, it's decreasing because as you increase your x value, the y values are going down. As you increase your x values more, they're going down, and then they're going up. Most of this analysis is thinking about changing your output values because, your x values, because if you think about what this is, let's say this is the function f of x. This graph is showing the values that this function outputs, the values that this function creates, and it starts with the x. That's why we always start by scanning left to right. Now that was a lot of information. In fact, it takes a lot of practice to get used to all this stuff, but keep trying it, keep asking questions about what you see, and as always, go blue.